Sometimes, the most ordinary things in our lives hide extraordinary behavior. Things like bending metal in extreme cold, or the way a frozen bottle bursts overnight in a freezer. These moments remind us that nature follows rules. Rules that might seem simple, yet occasionally they surprise us. Water is one of those surprises. From the largest glaciers to the smallest raindrop, water is everywhere. It shapes coastlines, fractures rocks, and sustains every living cell. But among all known liquids, it behaves in a way that has puzzled scientists for centuries. Unlike most substances, water doesn't shrink when it gets colder. It expands. That one property changes landscapes, influences life on Earth, and even makes our planet livable. To understand why this happens, we first need to see how water connects to a much larger system: the structure of matter itself. Everything around us is built from atoms arranged in countless patterns. When temperature drops, those atoms generally move less and come closer together. Cold makes matter denser. But water somehow defies that rule. As it freezes, it grows, pushing outward with enough force to crack rock, burst pipes, and float massive sheets of ice on oceans and lakes. So what makes water so special? The answer hides in the invisible geometry of its molecules, a small, quiet dance that determines the structure of ice. Let's step inside that pattern. A water molecule is made of 2 hydrogen atoms and 1 oxygen atom. The oxygen end pulls electrons a bit more strongly, creating an uneven distribution of charge, one side slightly negative, the other slightly positive. This gives each molecule a polarity, almost like a tiny magnet. Because of this polarity, water molecules attract each other. The positively charged hydrogen of one molecule tends to link with the negatively charged oxygen of another, forming what scientists call hydrogen bonds. These bonds are relatively weak compared to the forces that hold atoms together inside a molecule, but collectively they shape how water behaves. In liquid form, these bonds constantly break and reform. Molecules slip and slide, never locking into a set pattern. As water cools down, the movement slows, and the molecules begin to stabilize. But at around 0 degrees Celsius, something remarkable happens. The molecules arrange themselves into a solid structure: ice. Within this frozen lattice, each water molecule forms hydrogen bonds that hold it slightly apart from its neighbors. The pattern is open and spacious, almost crystalline, like a delicate framework of hexagons. And that open structure is the reason ice takes up more space than the water it came from. The same number of molecules now occupy a larger volume. This makes ice about 9% less dense than liquid water, and that's why it floats. When you see ice floating on a lake, you're witnessing a rare property in nature. Most substances become denser as they solidify and would sink once frozen. But for water, the opposite is true. The layer of ice on top insulates the liquid below, protecting ecosystems through winter. Without this behavior, ponds, rivers, and oceans would freeze from the bottom up, trapping and destroying aquatic life. Planet Earth, as we know it, might not be the same. Water's expansion when freezing also affects the physical world on a much larger scale. In cold climates, water seeps into cracks in rocks, freezes overnight, and expands, wedging the rock apart. Over centuries, this frost action helps carve mountains and create soil. On a much smaller domestic scale, it explains why a forgotten soda can in the freezer, or a frozen water pipe, can suddenly burst open. If we dig deeper, this story stretches across science, history, and even the shaping of human civilization. The way water behaves when it freezes has influenced navigation, agriculture, and climate patterns. During ice ages, expanding glaciers cracked mountains and ground stone into fertile soil. That slow geologic process built valleys, directed rivers, and defined where civilizations could flourish. Even on the microscopic scale, the structure of ice affects how we study materials, preserve food, or even search for life beyond Earth. Scientists analyzing icy moons like Europa believe that understanding water's peculiar behavior could reveal how frozen worlds maintain subsurface oceans capable of sheltering life. There's also a broader insight here about the unpredictable symmetry of nature. Water, one of the simplest molecules, contains deep complexity. By bending the usual rules of contraction and expansion, it demonstrates how small differences at the atomic level can ripple outward to influence entire ecosystems and planetary systems. In physics, chemistry, and biology, few materials have consequences as far-reaching as H2O. In the end, the reason water expands when it freezes isn't just about molecules forming a crystal lattice. It's about how fragile balances at atomic scales create the world we inhabit. The openness of ice allows life below to endure, and the weight of that small phenomenon shapes continents, climates, and civilizations. So the next time you hear ice crack across a frozen pond, or see frost trace patterns on a window, remember, you're seeing geometry in motion, the quiet structure that lets life persist through cold. A simple mystery of matter that turns out to be one of nature's most vital designs.